Hello guys, Sir DV again here. We now continue discussing some concepts on tension members. So to illustrate to you how the determination of uh, the strength based on LRFT and the AST method is, we consider here a connection, okay, uh, which is made by uh, staggered bolted connectors, and a partial figure of the member is actually illustrated here, and we are going to look into the uh, probable, okay, the most probable failure path that we can expect to happen here in our connection. Of course, this is only one part of the connection. The other part is assumed to be not critical. So we focus more on this part in order to demonstrate how these failures may happen here. Okay, so the plate section is fastened by 1-inch diameter bolts, and we are to analyze the limit state of the plate subjected to a tensile force T acting at the centroidal axis of the plate and the bolts as well. Okay, so the limit states are defined in our lecture uh, based on LRFD and AST. And the first thing we have to take note of course, is what is the gross area of the plate. Okay, so the gross area is a simple product of the width, the gross width, and the thickness. So it's 12-inch square. Also, for the diameter of the hole to be used in the analysis will be 1/8 inch larger than the bolt diameter. So this is 1.125 inches. So for the net area, only two failure paths are actually significant because the pattern is repeating. Okay, so and that is path ABCDE and path IJFH. Okay, so these are the paths we are actually referring to. So A, B, C, D, and E. Okay, and IJFH. Okay, so this path continuously going to F and then exiting at H. So the other path are possibilities which are the same as these two paths presented. Okay, whether you go here, you go here, you go here, you will notice that the path are just the same path as this one. Okay, whether you go here, you go here, and you go there, so this is just the same as this one. Of course, you have to take a look that the gauge distances G are given, and the uh, stagger distances S are also given in terms of the dimension. Okay, for the two paths, we are now going to use the formula we derived a while ago, uh, that your net width is simply equal to the gross width minus, this is the effect of the reduced bolt diameter, no? Okay, so summation ph plus summation s squared over 4g. So this is the one that I'm talking about here. Okay, so we just plug in all the necessary dimensions and given values in the problem. And considering that the path A, B, C, D, E have 3 holes and 2 stagger, we just take note that the hole here, the diameter of the hole will be multiplied by 3, and the staggering, which are uniform, will be not uniform. The stagger will be the same, so we simply multiply it by 2, okay, times this s squared over 4g. So where's that s squared over 4g? So I'm referring to this 2 stagger. So this is 1 stagger, wherein s is uh, equivalent to 5, okay, and your s is equivalent to 3, and your g is equivalent to 5, and the other stagger has the same s, which is equivalent to 3, and g equivalent to 5. So it's simply 3 squared over 4 times 5. So this is now 3 squared over 4 times 5, equivalent to 13.525 inch. So for the net area now, we simply multiply the net width multiplied by the thickness, we get a 10.144 inch square. So similarly for path IJFH, we have 2 holes and no stagger. So we simply do the same. So here, since there are no stagger, the formula for summation s squared over 4g will vanish. So this becomes 16 minus 2 times the diameter of the hole is 1.125. So we just get 13.75 as your net width multiplied by the thickness. You get 10.313 inch square. So the choice of looking into the weakest failure mode will be based on the lower value of the two net widths, and the lower value is 10.144, such that this value governs. Okay, so we're through with the net area. So the effective area then can be computed consequently using the formula an multiplied by the reduction coefficient u, where u is equivalent to 1.04 plates. So automatically u has no uh, reduction coefficient for plates. So the reason for that is since the plate element, so this is a section of a plate element, okay, when pulled into a connecting uh, let's say a connecting component here or member, since the plate thickness is almost the plate centroid is almost within. Okay, so this is now the shear phase, wherein the transfer of force from here to this component is due to the shearing effect uh, happening within this face. Okay, so since this plate has a very near location in terms of the centroid, then the shear lug effect is neglected. Okay, what's that shear lag effect? The shear lag effect simply is very high when the pulling force or the tension force is far from this interface. Okay, the connection interface or the shear face. Example, if I have an angle bar, let's say the angle bar is okay connected to a, a connector here by bolts. Say this by bolts, and the angle bar has a centroid somewhere here, which is now far from this interface or the shear face. So there's a considerable value of this distance x. Okay, so if this x is considerable, then the shear, okay, the shear force along the area of this angle bar will no longer be uniform. Okay, that's why that area is uh, reduced to an effective area equivalent to AE. So if I will draw now the shear stresses at this section, okay, so I will have a very high concentration of shear at this point, and then it reduces and lags at this point. Okay, so the concentration of the transfer of force becomes very small. Uh, sorry, it's the reverse. Okay, so this has a high concentration of stress. Okay, and it reduces like this, such that the effect of your total force T here will cause an even a varying distribution of stress, making your P over A erroneous. No, so your T over area becomes an error because it is concentrated more on the centroid rather than far from the centroid. So there will be now a reduction of area to compensate for the actual value of your stress when you compute the strength of the section. So that is how uh, uh, the shear lug effect is in consideration of your effective area. So the failure load's capacity is simply an application of the force of the formula we derived a while ago. So the failure load now, which is Phi is given by the yield, okay, the yield failure, the fracture failure, and the block shear failure, which if we just substitute the given values will yield to these values here, this value here, and for the block shear we will do this as a sit work. Okay, so for ASD we just use again the formula derived a while ago, So this is Tn is equal to 0.6 FyAg, Tn is 0.5 FuAe. We just plug in the given values we have, or sorry, the computed values we have solved, and then this is yielding, fracture, and there's no black shear in the AST. So what is now the final answer, final strength uh, you will be using for this computation. So we will do some more computations like this and verify how we get the governing strength of your tension member. Okay, so this procedure is just done to demonstrate how the two limit state procedures works. So the above procedure is done to solve tensile capacities, and if we are interested with the member safety, a comparison to the factored forces for LRFD and unfactored forces for ASD shall still be done, and take note that the failure path ABCDE carries more load than the rest of the failure pattern. Okay, so the ABCDE failure path for fracture is the most critical. Okay, so I hope you have I have presented the procedure on how to analyze tension members using both ASD and LRFD. Thank you.